Okay, let's see. A couple of announcements. You do have an initial homework assignment under homework and exams on eCampus. Homework 1. It is due September 12th, so not next week, but the week after. Let me know how it goes. Some of it I am open to making extra credit, say, if it feels like you aren't adequately prepared to do some of it. But it's intended to be a challenge, so it will probably be a challenge for you. But just holler at me if it's unrealistic for you to be expected to do it. If you feel like that's the case, every class is different. Big picture, what you're asked to do is, in the first question, download some data. So it says the oxygen data. On eCampus, under course content, there's a data folder. And any data set that I refer to by name in the class will be listed here. So download the oxygen data, and then in number 1, you're going to make some basic summary calculations, compute sample averages, compute sample standard deviations for each of the variables. It's a multivariate data set. You have P equal to 4 variables in the data set, multivariate. So for each one of them, compute sample average, compute sample standard deviation. Then make a couple of basic multivariate pictures. I'll say more about these types of pictures momentarily, but a pairs plot and a coplot. Your topic 1 lecture notes and your textbook have some definitions of what those things are, pairs and coplot. Number 2 is intimidating looking, but it's not actually technically hard to do, I claim. What it is some probability calculations and asking you to make use of the idea of distance. In multivariate analysis, we have multiple variables. And so we're going to be asking about how are these variables related to each other. What are the interrelationships, the co-relationships between our variables? A fundamental quantity for characterizing co-relationships will end up being distance. You're familiar with, say, Euclidean distance. If you have 2 vectors, what's the distance between them? It's component by component. Take the difference and square it. Add up all those squared differences, and then take the square root. Euclidean distance. In statistics, because there is the potential for different magnitudes of variation in the different directions, and because there's the potential for there to be correlations between the variables, correlations, it turns out that Euclidean distance is not the most natural distance to use for comparing, say, 2 random vectors or 2 parameter vectors. So instead of Euclidean distance, we're going to use throughout the class this idea of a statistical distance. This is topic 1 stuff in your lecture notes. There's also a section in the textbook about distance and Euclidean distance and statistical distance. This quantity right here, let me just write something on the board for us momentarily. Suppose we have 2 vectors, X is a vector that contains the entries x1, x2, and xp. And y is another vector. So vector for us is just a collection of measurements. Could be numeric, could be categorical. Let's suppose these are numeric. I have 1, 2, p variables in the y vector as well. Then the Euclidean distance looks like sum I equal 1 to p xi minus yi squared, and then take the square root. That's the usual way of a distance between two vectors. Another way to write that in more compact notation is the vector x minus the vector y transpose x minus y again, and then square root that. In your basic linear algebra, you learned how to multiply vectors, for example. One vector transpose multiplied by another vector is just the sum of the products of the components. That should be familiar to you. If it's not, then get some review going of basic vector and matrix operation. But Euclidean distance between x and y, one way to write it is this vector notation. X minus y transpose, x minus y, and then square root the whole thing. What we're going to call statistical distance is similar to this, but it's been fixed up a little bit to handle data. Statistical distance, as is in the slides, is of the form x minus y transpose x minus y, just like Euclidean distance, but then we weight the differences in the middle with a particular weighting matrix. So in the slides we have of this form. That's x minus y transpose times some square matrix sigma that's been inverted times x minus y again. It's just like the Euclidean distance, where we've stuffed in a weighting matrix at that red spot. I'll say more about this, but for now I'm just giving you a brief introduction to the homework. And in the homework, I'm asking you to compare Euclidean distance to statistical distance. All right. These parts, you may have trouble with these. They're not hard, I promise, or are not like technically hard, and they don't require any sophisticated calculation or programming or anything. They're mostly conceptual. So what I hope to happen is that we talk over the course of the next week. I help you on the discussion boards. I do the Q&A on Monday, and it clicks for you, and you're able to solve this problem. But number 2 is all about distances, and specifically how this statistical distance idea ties in with a common multivariate probability distribution, namely the multivariate normal. This is the probability density function for what's called the multivariate normal distribution. And notice that in its expression, right in the middle of it, is this statistical distance quantity. So statistical distance plays a key role in a lot of probability-based results for multivariate statistics. And number 3, I'm asking you to do very basic linear algebra calculations and assessments. I gave you a square matrix. That means the same number of rows as columns. And then I'm going to ask you, without using a computer, because I think this is a good exercise for you to make sure you really understand what an inverse is, what an eigenvector, what an eigenvalue, those things are, is to do it by hand. So for once in your life, do it by hand and find the eigenvalues and eigenvectors. Write what's called the spectral decomposition. Verify that the determinant of a square matrix equals the product of its eigenvalues. Verify that the trace of a square matrix equals the sum of its diagonal elements, and that the trace of A equals the sum of its eigenvalues. Is A orthogonal? Orthogonal is a definition. It's a type of matrix. So is it or is it not? Is it positive definite? And then find the inverse and the eigenvalues and eigenvectors of the inverse. Number 4 is just a kind of a cautionary tale. In number 4, I give you 2 matrices that are very, very similar to each other. If you compare A and B, first row, first column is exactly the same. First row, second column is exactly the same. Everything's exactly the same except for the second row, second column. And in that component, in that cell, there's a very minor difference between these 2 matrices. So just looking at it roughly, these are basically the same 2 matrices. And then I want you to compute the inverse of each of these matrices. And note that while A and B are nearly identical, their inverses are not. In particular, the inverse of A is approximately -3 times the inverse of B. Even though they're so similar, the implication is that small differences in beyond the decimal point, which can often happen due to rounding, for example, can have big-time impact on matrix-based calculations. Number 5 is some expectation calculations. Expected value, which is a probability calculation. So I want you to compute the expected value, which is the mean, and the variance, which is a different type of expected value, but it's still an expected value, of linear combinations of 3 random variables. So here's 3 random variables, x1, x2, and x3, like we would have in a multivariate data set. You have an Excel spreadsheet with individuals in the rows, and you have a column for x1, a column for x2, a column for x3, multivariate data. Those 3 variables are going to be allowed to be correlated with each other. That's what multivariate statistics is all about, is allowing for and incorporating correlation and covariance between variables. So with an arbitrary expression for the correlations and covariances between these 2, compute what's the mean of that and what's the standard or the variance of that. x1 minus 2 times x2. That's a linear combination of the 3 variables. Even though x3 is not in there, it's still a linear combination of all 3. It's just like we used the coefficient 0 in front of x3. Number 6 is for a bunch of different covariance matrices in the 2-dimensional case. Suppose our data is 2-dimensional. P is equal to 2. There's 2 columns in our spreadsheet. Here's a bunch of possible covariance matrices. And we'll say more about what a covariance matrix is soon. But basically, it's a matrix containing the variances of each of the variables in the diagonal elements. And in the off-diagonal elements are what are called covariances. which are related to correlations. So in this question, I'm wanting you to get a feel for what do bivariate distributions look like for different sets of covariance matrices. Just as a quick picture, suppose we have bivariate data, and I'm going to make a picture. Here's the first variable, here's the second variable, x1 and x2. If I had 100 observations, my sample size was 100. There's 100 rows in my Excel spreadsheet. Maybe I draw a scatter plot and see something like that. 1 point for every row in my data set. Because every individual is multivariate, I have 2 variables measured for every individual. I can make a picture of my whole data set in that case with a 2-dimensional scatter plot. A probability distribution in your intro stat class would say for a single random variable, there's some function, a curve, that dictates the probabilities that are assigned to different possible values of x. That's a univariate probability distribution function. If I wanted to know what's the probability x goes between A and B, for example, I would integrate this function, compute the area under the curve. That's a probability. We're talking multivariate stuff, so we need to think about a generalization of that type of thing. That's a one-dimensional probability distribution function. In multivariate world, we're going to be talking about multi-dimensional surfaces. So imagine that's like a contour map, and what that's representing is that there's kind of an elliptical 3-dimensional image coming out of the picture at you. We could try to draw it like something like that if we rotated the axes some. Instead of a bell-shaped curve like in the top right, in 2-dimensional space it's kind of a bell hat-shaped 3-dimensional surface. And if we have big data and we have 30,000 variables, it's a 30,000 dimensional thing. It's easy to visualize in 2 dimensions. That's why I want you to play with the 2-dimensional case a little bit here and just get a feel for what does bivariate data look like and what do the different distributions look like. And then number 7 is some more basic probability calculations, expected values, and covariances. Again, this should be a good challenge for you. If you need more time, let me know. Just give me feedback, and I'm a fair grader and prof, I promise. All right, what I wanted to do today is get started with some of our notes. I mentioned on Wednesday that the upcoming Monday, I can't give a live lecture. So what I'm going to do in place of a live lecture is post a recorded lecture, and the one I want to show you is actually on topic 1. The notes that I've given you that are called topic 1. I'll open these up briefly to give you the big picture. This is just like chapter 1 of our notes. And what it consists of is 2 basic sections, 2 main sections. First is kind of a survey of the whole class. We're talking multivariate stuff. What does multivariate mean? And what kinds of things can we do with multivariate data? So they'll be basically going through this set of 5 bullet points. Here are the things that we're going to learn about this semester. 1 is dimension reduction. That's like principal components and related ordination techniques for taking a high dimensional data set and cramming it down into a lower dimensional representation. As we talked Wednesday, the goal is to preserve as much of the information as possible. But go to a smaller dimensional representation so we can actually look at the data, make 2-dimensional scatter plots and stuff. Formal statistical inference, that's p-values and confidence intervals. So we're going to learn how to do multi-dimensional t-tests and multidimensional regression and ANOVA. Correlation, there's some specialized applications of correlation with multivariate data. In particular, we'll learn about canonical correlation. So we'll learn a lot about correlation. Discriminant analysis could also be called predictive modeling. I told you about this on Wednesday as well. So things like prediction, supervised learning, we will give some fair coverage in this class, and cluster analysis, clustering. And what comes in the remaining part of these slides for this section is just some real quick examples of what this stuff looks like. So that's going to be in your video on Monday. And then what I wanted to show you at the end here is that there's a section on distance. In your homework, there is a problem that's all about distance. There's Euclidean distance, there's statistical distance. So I will also give you in the lecture video me lecturing through this part of the notes. This will be familiar to what I ask you to do in the homeworks. Okay, but I don't have time to go through that set of slides today. What I want to do today is go through topic 2. Topic 2 is going to get us up to speed on the basic vector and matrix operations that we need for this class. What's an eigenvector? What's an eigenvalue? What are some of the key results that we're going to make use of? So in our remaining 25 minutes, let's see if we can get through topic 2 here. Our data are going to be, as a whole, represented as like a spreadsheet, Excel spreadsheet. Some number of rows, which is the individuals, and some number of columns, which is the variables. Any one individual is one row in our spreadsheet. That's one person or one device, one animal, one plant. It's whatever we're studying, it's one of them. For each one of them, we have a vector. Because it's multivariate, for each person in my study of breast cancer, I have age, I have BMI, I have a number of cigarettes smoked a week, stuff like that. Multiple variables for each person. So putting multiple variables into one item is turning the variables into a vector. It's just a collection of p items. Variable 1, variable 2, ... variable p. So a single multivariate measurement is a vector to us. And then a sample of multivariate measurements, like a spreadsheet full of our data, is a matrix. Two-dimensional array. So today I want to remind you of some of the core stuff of the basics of linear algebra. And then I want to introduce you to what we call a random vector and probabilities for a random vector. And what comes with a probability model is the ability to do expectation calculations, expected values, and variances. So I need to go through this pretty quickly. Linear algebra is a prereq for the class, so this should be review for you. There is additional review in the textbook. Here's a vector. We'll use boldface X to indicate a vector, in this case of n real numbers. So x1, x2, ... xn. I can assign all n of those to one single object, one single variable, if I represent them as a vector. Generally, we're going to represent a vector as a column. The observations are oriented vertically. That's a little bit counterintuitive to the way I've said our data sets are organized, though. Any individual, go back to my whiteboard. For us, a data set, let's call it X, is n by p, individuals by variables. So each row, well, let me ask you, just make sure everybody's awake. An individual, suppose we're studying breast cancer. We have 100 women in our data set, and for each woman, we have, let's say, 5 numeric variables. Their age, BMI, cigarette smoked, stuff like that. Individual or woman 12 is where in capital X? Where would I go to find? Say it again. Individual woman 12 is where? Okay, 12th row. If I were to go down 12 rows, all of the columns is for the 12th person. The vector of 5 things are the measurements, the 5 measurements for that individual. So in some respect, individuals are rows in our Excel spreadsheet. That's a little bit counterintuitive to what's said here. Each vector is going to be represented as a column. You'll pick it up as we go. We'll get practice, but just I'm acknowledging there's a little bit of a trickiness there. Individuals or rows are of our data sets. That said, any one vector, unless it's been transposed, should be thought of as a column vector. Here's a picture of a vector, three-dimensional, or a three-component vector. The vector is x, calling it x, and if I transpose x, that means I get to orient its entries horizontally. X transpose, then, I can write it as square brackets. Its first value is 1, comma, second value is 3, comma, third value is 2. And then you can visualize that on 3 dimensions. If you go out 1 unit in the first dimension direction, and 3 units in the second dimension direction, and 2 units in the third. You get this directed line segment or directed vector. Arrowhead is placed pointing right at the point that these coordinates correspond to. So in some sense, all of our individuals, all the women in our breast cancer study, are vectors. They're these little things pointing out in multidimensional space. If you multiply a vector by a constant or a scalar, then that just means you multiply each component of the vector by the scalar. So C, if it's just a constant scalar times x, all the components of x are just multiplied by C. That's a picture of that. X is, the original vector x is the solid directed line segment. And then C, where 2x is, that's the result of multiplying the x1 and x2 coordinates by 2, each of them. So x1 becomes 2x1, and x2 becomes 2x2. So that vector is now 2x. You can multiply by negative numbers as well. Here's the result of doing minus 1/2 x. Vectors are these things pointing off into multidimensional space. You can multiply scalars by them to expand them and contract them, or change the direction of them. You can add vectors as long as they have the same number of components. If I have 5 variables for individual 1 and 5 variables for individual 2, it makes sense to say individual 1 plus individual 2. When you add 2 vectors, you just add component by component. So x plus y is component 1, x1 plus y1. Component 2, x2 plus y2, dot, dot, dot. There's a famous parallelogram representation of adding vectors. This is a picture that you've probably seen in junior high or high school. X is a vector, Y is a vector, and if you add them together, X plus Y is this diagonal of the resulting parallelogram that's created. And all that is a picture of what was on the previous slide. X plus Y is component by component add. We will often talk about the magnitude or the length of a vector. How long is a directed line segment? The definition is it's add up the squared values of the components and then take the square root. So if you have a vector x that originates at the origin and goes out in some direction, x1, x2, x3, all the different components, then its length is given by this expression. You add up the squares of each of the components, take the square root. The inner product of two vectors, x and y, what kind of arithmetic can you do with two vectors, x and y? We just saw we can add them. We saw we can multiply them by scalars. And in some sense, we can multiply two vectors by each other. You have to be careful about what you mean by that. One way to, quote, multiply two vectors is with this inner product operation. So what it is, x inner product with y, is component by component do multiplication and then add them all up. So if I have 5 variables, I do individual 1 variable 1 times individual 2 variable 1. And then add that to individual 1 variable 2 times individual 2 variable 2. And add that to ... Inner product is just component by component multiplication, and then you add all those up. Shorthand representation of an inner product is of this form: x transpose y, or x apostrophe y. The apostrophe after a vector means transpose. So we said that by default, our vectors are going to be viewed as standing vertically, like a column vector. Like x is of this form. The transpose operator, if I transpose x, that switches this from being oriented vertically to being oriented horizontally. The values themselves are not changed. It's just the orientation. If I do x transpose y, the inner product of x with y, what that looks like is x1 through xn oriented horizontally mashed up against y1 through yn oriented vertically. That's actually a special case of a matrix multiplication that we'll see in a second. Matrix multiplication. You can do arithmetic with matrices. And the way you compute this is you go component by component. I would say x1 times y1 plus x2 times y2 plus ... So in short, it is the sum from I equal 1 to n of the component by component products. Today's going to be a little bit dry, sorry, but we need to have our core toolkit of tools to play with before we can do the fun stuff. I'll skip that. It is possible to, well, I'll skip it for now. It is possible to compute angles between vectors, and that is relevant to some of the things we're going to do this semester. Maybe I'll come back to this later. I'll keep going. This is important. Linear independence. Okay, so suppose we have a set of vectors, x1, x2, dot, 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 xn. Every one of those is the same size, same dimension, has p variables in it, say. We're going to have that a lot throughout the semester because whenever we have a data set, we're going to represent it as I have n observations of a multivariate random vector from some population. If it's the breast cancer example, I have 100 women. I have x1 for woman 1, x2 for woman 2, dot, 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 x100. And for each one of them, I have a vector of observations. So we're going to be saying our data sets, our samples, look like x1, x2, dot, 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 xn, where each of those is a vector. An important characteristic of a collection of vectors is yes or no, are they linearly independent of one another? Basically what this means is there redundant information in and amongst my n vectors? If one of the vectors is equal to one of the other ones, for example, suppose woman number 1 has the exact same 5 variable values as woman number 10. Then I have no additional information from adding woman number 10 to my data set because they are the exact same data. That redundance will translate to problems for statistical methods. When it comes time to computing covariances and inverting them and stuff like that, we'll get errors out of R. So we need to be aware of this issue that can happen, and we need to be able to diagnose if it has happened for our data sets. So linear independence, x1 through xn, are linearly not independent, or in other words, linearly dependent, if there is some collection of constants that are not all 0, such that the linear combination of the x's using those constants equals the 0 vector. May or may not sound intuitive to you. Doesn't usually sound intuitive to me the first few times I see it. But if you think in terms of, can I rewrite one of my vectors as a linear combination of the others? If individual 1 is exactly the same as individual 10, then obviously individual 10 is a linear combination of all the variables. 1 times individual 1 plus 0 times everybody else. That's a linear combination. That's like an extreme case of linear dependence when two of the individuals are exactly the same. More generally, we still have that problem, that issue, if any one of the columns can be written as a linear combination of the others. It's hard to visualize. What I want you to take away conceptually is that the thing we're trying to characterize and deal with here is the possibility of redundant information. If you have the same data set or the same observation multiple times, it's like you're double counting the same thing, and it doesn't work. The methods will break for us. I encourage you to go through an example or two. There are some examples in your book. Here is a very simple set of 3 vectors that happen to be linearly dependent. How do you find out if they are? You try to set an arbitrary linear combination equal to 0 and solve for the coefficients that make that true. If you can find a solution to this equation without using all the c's equal to 0, then you have discovered linear dependence. If there is no solution to this, short of using all zeros for the coefficients, they are not linearly dependent. They are linearly independent. I'll skip this for now. I do want to say something about matrices before we finish today. That was all about vectors. Individuals in our data sets are going to be represented as vectors. Woman 10 is the vector of 5 observations. Similarly, variable 4 can be viewed as a vector of n observations. If you slice the data set, the matrix, horizontally, you're picking out individuals and all p variables for them. If you slice it vertically, you're picking one variable and all the observations on that variable. So a matrix, call it A, is a two-dimensional array. And we're going to use this type of notation, boldface A, and often we'll have underneath it written its dimensions. So the n cross p means n rows and p columns. You'll see notation like this throughout the class. A11 indicates first row, first column, the value that happens to be in the first row, first column. Whereas A2p is the second row, pth column. Generally, Aij is the ith row, jth column. Just like we could transpose a vector, we can transpose a matrix. That should be familiar to you. You switch the rows to be the columns. You can add two matrices. If they have the exact same dimensionality, n and p are both the same, it's a 3 by 2 and a 3 by 2 matrix, say, you can add them, and all matrix addition is component by component addition. If I have two 3 by 2 matrices and I want to add them, I result in a 3 by 2 matrix, and each element is just the sum of the corresponding elements of the two matrices that I was adding. Just like we can multiply a vector and it stretches or contracts or switches the sign, we can multiply a matrix by a constant. And it's an analogous effect. You just multiply every single component of the matrix by that constant. Slightly more complicated is if we want to multiply two matrices. Again, I hope this is fresh for you. But if you have two matrices, A and B, there is a defined operation called the matrix product, A times B. The main thing to, I guess, be aware of when you're doing matrix multiplication is that the dimensionalities have to match up just right. If A is n by k, that's n rows, k columns, and B is k by p, that's k rows and p columns, that's where you're able to do the matrix multiplication. They're not necessarily the same exact dimension. The key is that what's on the left side of the multiplication has the same number of columns as what's on the right, as the number of rows for what's on the right. Matrix multiplication we'll see throughout the class. Here's an example. Okay, we're almost out of time. I want to definitely show you eigenvectors, eigenvalues. So eigenvectors, eigenvalues, these are these magical, mysterious quantities that are really hard to explain in plain English, but that they're going to show up over and over again throughout the class. You've heard of principal component analysis, many of you. All that is eigenvalues, eigenvectors. Linear discriminant analysis has a close relationship to eigenvectors, eigenvalues. A lot of multivariate statistics is eigenvector, eigenvalue stuff. So what is it? Big picture, eigenvalue, eigenvectors are like a core representation of a matrix. We're going to be interested throughout the class in a particular kind of square matrix. It's going to be called the covariance matrix. And we'll call it P by P. We have our capital X data set, N by P. That's N individuals for each of whom we have P observations. So we have P variables. We can characterize the variation and the covariation, the interrelationships between and among all of those P variables, succinctly with what's called a covariance matrix. We have P variables. Inside the P by P covariance matrix, the diagonals are variances. So in the first row, first column is the variance of the first variable. In the second row, second column is the variance of the second variable. Dot, 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 way over here is the variance of the pth variable. And in the off-diagonal elements, these are called covariances. P by P, the diagonals are all the variances, and the off-diagonals are covariances. We'll define covariance soon, but think of it as an unscaled correlation. Correlation is like a measure of linear association. If two variables tend to vary together, that means as one variable gets big, the other tends to get big. If they vary in an inverse relationship, as one gets big, the other tends to get small. But there's a co-relationship if they vary together. Okay, we're out of time. We're going to be looking hard at these covariance matrices. And for the purposes of discovering important patterns, we're going to wish we could take this matrix and break it down into core components, its very essence. And it turns out that roughly speaking, let me say, can be characterized essentially using eigenvectors, eigenvalues. I'm going to call it the Eigen Decomposition. All that means is I can take that capital sigma and decompose it using math into these two quantities, the eigenvectors, the eigenvalues. What's great about doing that is that it gets us towards dimension reduction, because there's going to be some eigenvalues, eigenvector pairs that are most important in representing sigma. And there's going to be others that are much finer detail, maybe can even be ignored. Okay, so I'll pick back up there Wednesday. I'll post, I hope today, maybe over the weekend, a video for you to watch in place of the lecture Monday. I recommend that you get cracking on the homework. One last announcement I forgot to make. I posted on eCampus this afternoon under discussions, general discussion, R tutorials. I mentioned some of this, I think, on Wednesday, but the R cookbook is good for getting up to speed on basics of R. At codeschool.com, you can create a free user account, and there's a tutorial called Try R that's good. And then at lynda.tamu.edu, you can log in with your UIN credentials, doesn't cost you anything, and there's a good training tutorial video on R called R Statistics Essential Training. Okay. Got it perfectly. Have a good weekend. Thanks.